Hey, so this is presumably our last talk of this workshop. It's my pleasure to introduce Petra Wolf, who is going to talk about generalizing temporal exploration problems. Please, over to you.
Okay, thank you very much. So this is joint work together with Emanuel Arrighi, Fedor Fomin, and Petra Golovach. And I'm especially happy that I was invited and can present this paper here because it was basically inspired by the workshop last year. So it's kind of like coming back to the questions of last year. And I also start with saying which setting of temporal graphs I precisely consider. So I have the setting that a temporal graph consists of a sequence of snapshot graphs that are all explicitly given in the input. And all of these snapshot graphs share a common set of vertices. And I will call the length of the sequence of snapshot graphs the lifetime of the graph, and the underlying graph being the union over all snapshot graphs. And we will use this number m here, which denotes the number of timed edges. So the sum of the size of the edge set over all snapshot graphs. And now the problem that we're interested in is to find a non-strict exploration. So this means we want to first visit all of the vertices by a non-strict temporal walk. What is a non-strict temporal walk? It is a walk such that in each component, in each time step, we can visit all vertices of the component that we're currently in. So for instance, if we start in this vertex here, in the first time step, we can go along all the edges that are currently there and pick some vertex where we want to wait for the next snapshot to arrive. Then in the next snapshot, we can again visit all of the edges that are currently, across all of the edges that are currently there. Pick a vertex to wait for the next time step, and so on. So thereby, this is a non-strict temporal walk, which was already defined more formally multiple times during the day, so I will not do this more formally. And what we try to find is a non-strict temporal walk that starts in a given initial vertex and visit all vertices of the graph. So more formally, the input is a temporal graph. And the start vertex, the question is, does there exist a non-strict temporal walk that starts in the start vertex and visit all vertices of the temporal graph? And then we also considered more general versions of the problem, namely what we call k-arbitrary non-strict temporal exploration, where we don't ask to visit all of the vertices, but at least k many of them, and an even more general version, for which we then also give the kernel, which is weighted k-arbitrary non-strict temporal exploration, where we have also a weight associated to the vertices of the temporal graph. And then we want, and an integer k as the input, and then we want to know whether there exists a non-strict temporal walk that visits vertices with total weight at least k. And now I want to come back why this is related to the iteration of this workshop one from last year by going over the history of the problem. So for the strict setting, the temporal exploration problem was introduced by Michael and Spiraklis, who showed that the problem is NP-hard. And then Erlebach and Spooner introduced the non-strict temporal exploration problem and also showed that it's NP-hard. And then later considered the parameterized complexity of the problem and showed that non-strict temporal exploration is FPT in the parameter lifetime of the graph, and the k-arbitrary non-strict temporal exploration problem is FPT in k. And Thomas also presented this work on at this workshop last year, where he stated the open problem, whether non-strict temporal exploration is FPT or at least XP in the parameter maximal number of connected components per time step, and also whether k-arbitrary non-strict temporal exploration is FPT in parameter lifetime. And I was listening to it and was like, that sounds like a nice problem. I want to solve it. I was thinking about it for some weeks, and then I could figure out that the answer is no to both questions. So it is actually, and as temporal acceleration is actually NP hard for a constant number of connected components per maximum number of connected components per time step, and K arbitrary N as text is W1 hard in the parameter L. So this means here are no additional FPT results to obtain. So we thought, okay, how can we improve the known results further then? And then the idea was to look into kernelization. But then it turned out that for all of the parameters that Thomas and Jacob looked at, there does not exist a polynomial kernel under some complexity assumption. So this means that all of these parameters here don't suffice to give enough structure to be able to get a polynomial kernel. And as you see, the parameters are basically more or less the dimension. If you think about a temporal graph, vertices on one side, lifetime on the others, it's basically the dimension of the temporal graph. And it does not take into account at all the structure of the graph. So what we try to do then is to get some insights in the structure, and if we can obtain a polynomial kernel by also taking into account the structure of the graph. So therefore, some simple structures first. So assume that we have that the underlying graph is a path. Well, then it's easy, because the best thing you can do is pick a side, go all the way to the one side, and then go all the way to the other side. Then another simple structure is a star, where if you don't already start in the center, what you do is you go to the center and then you wait for the rays to appear, and then you visit the vertices at the rays, and then you go back to the center, wait for the next time step, and so on. So those are simple structures where we can solve the problem in polynomial time. But what happens if we combine them? So if we have two stars with a bridge in between, well, it turns out that then the problem is again NP complete. And this is really very simple tree. It's basically just two stars with a bridge. So this also rules out all structural parameters of the underlying graph, like path width or tree width or whatever. Okay, so then the next thing we were thinking about, okay, what if we restrict how often an edge can appear? But then it turns out that the problem is, again, NP complete, even if each edge appears only once. But if you combine these two properties, so if you combine to have the structure underlying graph being a tree, and each edge appears only once, then the problem is solvable in polynomial time. So our idea was to construct a parameter that describes you the distance to this property, which we defined as, we call it P, which is, remember, this was the number of timed edges minus the number of vertices plus 1. So it is basically how many timed edges do I need to remove to end up with a forest where each edge appears only once. And for the following, we will call edges that appear only once, we will call them blue edges, and edges that appear at least twice, we will call red edges. Then the first observation is that the parameter actually bounds the size of a feedback edge set of the underlying graph that further contains all red edges. So this means we can think of our temporal graph as being of this form, where you have a set X that is on one side a feedback edge set of the underlying graph, and that also contains all red edges. This means everything that is left outside of this set X is only trees on blue edges, or this path here, where on the path you have again trees, blue trees attached. And everything outside here, we know that these edges appear only once. And we can show that we can find such a set X of size linearly in our parameter. Okay, So now we want to give a kernel for this. So this means we need to reduce the instance such that in the end, the size of the instance that we obtain is bounded in a parameter only. And the first thing that we consider is how to get rid of this, of too many of these blue trees hanging around here. So consider we have some vertex x in the set big X. And this vertex now has a lot of blue trees hanging outside of the set attached to X. And it also has some edges to other vertices in the set big X. So if we now have too many of these trees hanging around, then we have some trees where the single appearance of an edge connecting to X is between two appearances of edges to the left. And if we now enter any of these trees hanging here, then we wait for the next one to come up, then on this we have no choice but to wait on the vertex X, and we cannot go anywhere else here in the set because there is no edge appearing here, because we are bounding the number of edge appearances in the set X by our parameter. So this means that if this here is more than our parameter, then we have multiple of these trees appearing between consecutive appearances of edges here on our vertex to the left. And this means we have no other choice than to wait on X, and hence we can also just collapse this tree and replace it by a path of length 2, where we put on the first vertex here the weight that we can obtain by entering the trees and going back to the set X so that we can continue our exploration, because remember, this edge only appears once, so we cannot wait anywhere in this tree here, because then we could not go back to explore other things anymore. So this weight we put on the vertex Y, and on Z we put the maximal weight that we can obtain if we end our exploration in the tree. So if we don't want to go back to X. Okay, and with this, we now know how to deal with these trees hanging around. And that we can replace them by paths of length 2. And we can also reduce the number of trees, because if we're stuck on X between multiple appearances, it's basically the same thing. So then the next thing we have to deal with are these paths connecting where the two endpoints of the blue paths are in the set X. And we also have trees hanging around on this path. So then we have multiple cases that we need to consider. The first one is that if some edge in the path, their single appearance is actually before the appearance of the edges connecting the path to the set X, then we can actually never use this edge here, because once at the time that we can actually go into the path, this edge already appeared and will not come back again, so we can simply remove it. And if we remove this edge, we cut the path apart and we are left again with trees, and we know how to deal with them. So then the next case is that we have consecutive edges in the path appearing at the exact same time step. So this means in this time step, we can either be on this vertex, or on this vertex. And then we can reassign this edge here to be connected directly to the set X. Thereby, we shorten the path here and cut out the tree. Okay, we know how to deal with trees. But importantly, we shortened the path here. And now we have again that we can basically be in this vertex and this vertex, or in this vertex at the same time. So we keep this property, but we get rid of consecutive edges having the exact same time step. So then the last case that we have is that we now have a path where the time labels are monotone, so that we have a strict monotone increasing. So for instance, from V0 to V5, we have first this edge, then the next one, then the next one, then the next one, and so on. And now we have three cases how we can go through the structure. One is we can, okay, actually plus ending. So and on one side, we can enter at V0, do some exploration and exit again at V0. This then needs to be all at the same time step here in the tree. The other thing is we enter at V5, do some exploration and exit again at V5. And the next one is we enter at V0, go along the path here and exit at V5. So now we want to replace this big structure here by something smaller, preferably of constant size, that keeps us the information of these three options. Therefore, we replace the structure by 3 vertices only, where on the first one up here, we put the weight of entering at V0, exiting at V0, on the lower one, entering at V5, exiting at V5, and on the middle one, going through the whole path. And now, as before with the trees, we also have the option of actually ending our exploration somewhere in this tree here. So we also add the vertex that represents the weight that we can obtain by entering at V0 and ending the exploration somewhere in the previous structure. And the same thing for V5, entering at V5 and ending the exploration. So here I'm a bit hand-wavy because you need to take care that you don't double count things. So you need to subtract options again. But this is basically the net gain that you can get in these different options. So now we also know how to deal with the structures path with trees hanging around. And these are now all our structural modifications that we do in our kernel. But as we replaced an arbitrary large structure here with something constant where we kept the sum of the weights, we now could have that our weights are arbitrarily big and no longer bounded by the parameter. So we also need to deal with that. And therefore, we use the result of Frank and Tardos as a black box. I don't want to go into detail what this means, but intuitively, it can be used to compress your weights again. It's basically a result on vectors that you can shrink the values and still have some the comparing of the entries available. And with this black box tool here, we can bring down our weights again so that they're bounded by the parameter. And the last rule that we have is, as we removed the timed edges, it could be that now some snapshots become empty. And the last thing we do is we simply remove empty we remove empty snapshots and we shorten the lifetime accordingly. And with that, we are done. And we obtain a kernel of size p to the 4, where the 2 to the 4 only comes by the blow up of the weights. So the 2 to the 4 is by the by this black box tool that we have. And the graph that we obtain actually has linearly many vertices, edges, and lifetime. So, and now I already want to end with some concluding remarks. First of all is that most of our results also hold for the strict setting, including with some easy adaptation, kind of in the sense that we heard in the previous talk. And this also applies for the kernel. And now we introduce kind of a new parameter. So the question is this parameter also useful for other problems? We think so, especially to obtain polynomial kernel, because we already know that it's kind of hard to get FPT results for temporal graph problems because things often are more complicated than in the static case. And this is even more the case if you try to get kernels. So therefore, the question is also, what are actually good parameters to obtain kernels for temporal graphs? And with this, thank you for your attention. And yeah.
Are you aware of the complexity problem in ICALP?
I guess with cycles, it's the same thing. You either like with, I guess it's similar to paths.
But can't you switch your direction and go the other way around to take the next vertex, then go somehow back and forth?
Yeah, but wouldn't this just be that you have kind of a linear option of where you cut your cycle and then it's a path?
Maybe.
So intuitively, I would say it's similar to paths thereby.
Okay, so in this case, might be a parameter like max leaf number be of interest. So essentially, in this case where you had the two stars connected by an edge, your max leaf number just is roughly n.
Yeah, maybe. But now you could in this construction simply extend the stars to put an arbitrary big tree on there to blow up your size compared to your number of leaves. Or what do you, maximum? What exactly is maximum leaf number? Is it just like
maximum number of leaves of any spanning tree of your underlying graph?
Yeah, but you can. Yeah, okay. Feeling-wise, I would say it's still hard because you can change, you can add so much stuff in there, and the construction still works.
Okay, thanks.
Any other questions?
I wanted to ask, your kernelization result uses a lot of space, from what I understand, for the weights, right? So
Sorry?
Your kernelization result uses a lot of space for the weights themselves.
Mm-hmm.
So this means that for the unweighted problem, you wouldn't be able to simulate weights by effectively encoding them in unary and subdividing edges, right? Have you looked at kernelizing the unweighted case?
So for the unweighted case, if you want to explore everything, so it's not K, but you want to explore everything, there we have a linear kernel. But in order to get a kernel for the K variant, where you just want to visit not all vertices, but K vertices, there we needed to go to the weighted case to obtain a kernel. At least we couldn't manage without going to the weighted case.
Right. Also, I'm not familiar with the framework of kernels that much. Is it possible to prove a negative? So can you prove that there doesn't exist such a kernel in the unweighted case? Or is that just sort of a conjecture that has to stay a conjecture?
So for the unweighted case, we did not prove that there is no polynomial kernel, but there is a tool. There are some tools to show that there is probably, under some complexity theoretic assumptions, no polynomial kernel. This it's basically a self-compression where you, it's called a cross-composition, where you reduce multiple instances of an NP-hard problem into one instance of your problem without blowing the parameter up too much. And if you can do this, then there cannot be a polynomial kernel. So
okay, cool.
You combine these multiple instances with an OR. And if you manage to do this reduction, then there is probably no polynomial kernel, where we also had, I think I have it here again, where we also have several results where we use exactly this for this kind of dimensional parameters.
Gotcha. All right, thanks.
Thank you, Dave.
The first question.
Okay.
Any other questions from the online participants? Okay, if not, then let's thank the speaker again. And let's thanks to all the speakers of today's workshop, and also to all the participants for attending this workshop. It was very nice having you. Maybe some final remarks from George.
Yeah. Well, thank you, Petra. Thank you, everybody, for for coming online or offline. We had some kinds of accidents, some missing flights, whatever. But finally we made it.